Hi grade 11s and welcome to this video. In this video, we'll be working on the Mathematics Paper 2 for June 2024, and this is specifically from KZN. Question 1 says, in the diagram below, D, which is negative 10 and 6, E, F, and G are the vertices of a quadrilateral. F is a point on the x-axis, and then they tell us that the diagonals of the quadrilateral bisect each other at K. I've seen this question before. Okay, let's just see. The equation of diagonal EG is 3x minus y plus 6 equals 0. Okay, the reason I say I've seen this question before is because if you check, you will find that on this platform, there is also an exam paper with this exact question. You would probably remember that. And they also say beta is the angle of inclination of EG. And the first question, they are also asking for the size of beta. Okay, so let me go ahead and show you the question paper that this is a clear copy and paste from. We can even just look at the other questions and just to see whether it is. Yes, and then the last question was to prove that the shape was a rhombus. Okay, so do you see what I mean by this? This is from this paper. This is from the provincial exam, grade 11, June 2023 from Gauteng. And if you go to question 2, this is a copy and paste of this exact question, okay? There's some things that have been changed here and there, like instead of saying F is a point on the x-axis immediately, here they started by telling you the equation of EG was, you see, 3x minus y plus 6 is equal to 0. The exact same thing. Okay, the diagonals also bisect each other at K, but here they say at point K. Okay, here they just say at K, and then there we go. So everything's exactly the same. The questions are also identical. Okay, determine the size of beta, calculate the size of beta, calculate the coordinates of F. If equation DF, okay, is this, there, calculate the coordinates of F, given the equation of DF is that. Calculate the coordinates of E, calculate coordinates of E, prove that DEFG is a rhombus, prove that DGFE is a rhombus. Okay, so this one just said DEFE. This one said DGFE. So they're perfectly identical. So for this one, I'm going to input this question's explanation. This was the 2023 exam, and then this was 2024. So you can see how that was just copied. It was identical. They didn't even change the questions here. Okay, the only thing different is really the mark allocation. Here, that was 2 marks, there was 3 marks. Okay, so I'm going to input that explanation, and here you go. Question 2 says, in the following diagram, D is negative 10 and 6, E, F, and G, which is 1 and 9, are vertices of a quadrilateral. The equation of EG, so this line, I'll just put that down, is 3x minus y plus 6 is equal to 0. You can see it's not in the standard form of the equation of a straight line. The diagonals of the quadrilateral bisect each other at a point K, as we can see. And then they tell us that the point F is on the x-axis and beta is the angle of inclination of EG. Okay, the first question is to determine the size of beta. So to find the angle of inclination of a line, you need the gradient of that line, okay? Because the gradient of the line is the change in y over the change in x. And these are the proportions for tan, okay? So tan theta equals the opposite over the adjacent. If you have a triangle and you take a right angle triangle specifically, okay, and you have an angle, you see that if you take the opposite side, that is the change in y, okay, from that top y and then that bottom y, over the change in x, that's the adjacent side, that is tan. Okay, so tan theta, that's how we find this. So we say tan theta equals, and let's go ahead and find this. So tan theta equals the gradient. We need the gradient. To find the gradient of this line, it needs to be written in standard form. So it's currently 3x minus y, and that was a plus 6 equals 0. And all we have to do is make y the subject so that it's in its standard form. Y equals mx plus c. So you can see that y here is negative. Just transpose it, becomes positive. And now we have 3x plus 6. So we can see that the gradient of this line, EG, is simply 3. Okay, so y equals mx plus c. So it's 3 therefore, to find this beta, we say tan beta equals this gradient of 3, and then transpose tan to get beta alone. So we're going to say on our calculator, the second function of tan, and then we'll say 3. So let's find this. So on the calculator, we say shift tan of 3, and there we go. It is 71.57 degrees rounded off to 2 decimal places, and that is our answer. Moving on to the next question. Question 2.2 says, calculate the coordinates of f given the equation of df is this. Okay, so the equation of df, and so you have to find the coordinates of f. F is on the x-axis, meaning this is an x-intercept. To find an x-intercept, you simply make y equal to 0, because at that coordinate, okay, on that coordinate, the y value is 0. So we have x plus 3y equals 8, and we're trying to find the x-intercept, so we make y equal to 0. And so that just becomes 0, and x is equal to 8. So it means that that point, f, is actually 8 and 0. So y value 0. You can also make sure you put that down because it's probably going to be helpful. Okay, moving on to the next question. Question 2.3 says, determine the coordinates of E. Okay, let's just see where E is. E is over here. And okay, so you see what we can do here. Do you remember how they said the diagonals of the quadrilateral bisect each other? So despite the fact that they didn't tell us what kind of quadrilateral this was, they didn't say it was a parallelogram, but they did say that their diagonals will bisect each other. So this is what it means for diagonals to bisect each other. If diagonals are bisecting, then it means that this line EG is cutting this line DF into 2 equal parts. So this is equal to this. Okay, so DK equals KF. And DF is also bisecting EG. So that cuts EG into 2 equal parts, meaning EK equals KG. So because of that, it means that the midpoint of this line EG is K, but that also means that the midpoint of line DF is also K. So they share the same midpoint. So the goal is find K, and that will help you find E. We can find K right now because we have D and F, those two endpoints. So let's use the midpoint formula to find K, and then we would find E. Okay, so using those 2 points, let me put those points down. Okay, so the midpoint of DF, we would find this by saying x1 plus x2, so this is just the midpoint formula, over 2, and then y1 plus y2 over 2. And so K, that midpoint, is simply found by saying, we can take this as the first point, negative 10 plus 8 over 2, and 6 plus 0 over 2. Okay, if you say 8 minus 10, that gives you negative 2, divided by 2 is negative 1. And then 6 divided by 2 is 3. So this is K. So K is negative 1 and 3. But here's the thing, we know that the midpoint of DF is exactly the same as the midpoint of EG, because they told us the diagonals bisect each other. So therefore, to find that coordinates of E, those coordinates of E, we can say to find this, we're using the midpoint of EG. And to find this, we would say x1 plus x2, but let's just use these. So we don't know what this is right now, so you call it x and y. Okay, so we're using x and y and 1 and 9 as E and G. So this means x1 plus x2, that's going to be x plus 1 over 2, and then y1 and y2, so y plus 9 over 2. But we know now that the midpoints are the same. So it means that the midpoint here is also K, which is negative 1 and 3. And so because they're equal, we can equate these. We can make their x values equal and their y values equal. Because on one hand side, we have the actual midpoint. On the other hand, we have the calculation for the midpoint. So they represent the same thing. So this means that this x value of x plus 1 over 2 is actually equal to this x value of negative 1. And this y value of y plus 9 over 2 is actually equal to the y value of 3. And so now we can solve. So you can see that you can't put this over 1, to create a fraction and then cross multiply. Or you could just see that 2 is in the denominator here. And we can multiply both hand sides by 2 to get it out of there. Now we have x plus 1 is equal to negative 2. And then transpose the 1. So x is equal to negative 3. And then here, same thing. Okay, here if you cross multiply, you're just going to say 2 times 3 is 6. And y plus 9 times 1 stays y plus 9. Then transpose the 9. So y is equal to 6 minus 9 equals negative 3. And there we go. E is finally negative 3 and negative 3. And that is our answer. Moving on to the next question. Question 2.4 says, prove that DGFE is a rhombus. Okay, so to prove a rhombus, here's how we do this. You would have to first prove that a shape is a parallelogram before you can consider it as a rhombus. So with this shape, proving it's a parallelogram is actually, it's fine because they already told us that the diagonals of the quadrilateral bisect each other. Okay, one of the ways to prove that a shape is a parallelogram is if the diagonals bisect each other, meaning they have a common midpoint. Then it's already a parallelogram. So now to prove that it's a rhombus. Once you have proven it is a parallelogram, you can prove that it's a rhombus using one of the following options. So these two options. You can either prove that those diagonals, they actually bisect at 90 degrees. Then that makes this a rhombus. Or you can prove that a pair of adjacent sides, one pair of adjacent sides are equal. Okay, so you can choose which one you want to use. Now, I would rather go with the proving that the diagonals bisect at 90 degrees because to do that, to show that diagonals bisect at 90 degrees, or in other words, diagonals are perpendicular, you can just use the property of perpendicular lines, which is that if you take the gradient of the first line multiplied by the gradient of the second line, if these lines are perpendicular, the product of the gradients is -1. And I know we found the gradient of one of these lines already, okay, one of the diagonals, which was this, EG. So see, that's already done. All we have to do is find the gradient of this line. Okay, so I would still confirm first that it is I will still conclude that it is a parallelogram first, okay, because of the diagonals bisecting each other. Okay, so it's a parallelogram because the diagonals bisect each other, and then further prove that it's a rhombus. So we already have the gradient of EG. Okay, we found that initially in the first question. The gradient of EG is 3. Okay, and all we have to do is find the gradient of the other diagonal. The other diagonal is DF. So use D and F, and let's put those points down. The gradient is found by saying the change in y, so y2 minus y1 over x2 minus x1. So this is equal to, and we're going to say 6 minus 0 over -10 minus 8. So this is positive 6. This becomes -18. And you know that 18, okay, 6 goes into 18 3 times. So this is -1 over 3. See how this makes a lot of sense. So the gradient of DF is -1 over 3. So now this is all we have to do. We can show them that if you take the gradient of EG and you multiply it by the gradient of DF, look at what they give us. 3 times -1 over 3 equals -1. Okay, so because the diagonals are perpendicular, what it means is they bisect at 90 degrees. So I'm just saying that DF is therefore perpendicular to EG. And finally, we can conclude that DGFE is a rhombus because the diagonals specifically bisect at 90 degrees. And that is our answer. Okay, so to prove a shape is a rhombus, you prove it's a parallelogram first, and then one of those two properties. Okay, grade 11s, as you see, the exam questions were exactly the same for that. Okay, so just remember that is it for question 1. Question 2, and it says, in the diagram below, we have A, which is -2 and -1, B, -3 and 4, and C, 1 and 5, are the vertices of a triangle. BC is produced to D, which is 5 and Y. And then they say AC cuts the Y-axis at F, and E is a point on the X-axis, such that CE is perpendicular to the X-axis. Okay, so you can see these two, okay, because they lie on the same vertical line, it means they're sharing the same X value. Okay, so if that's 1 and 5, this is 1 and 0 because it's on the X-axis. So this also looks very similar to the 2023 exam paper from Gauteng. So I'm just going to compare them as well. Okay, so you will see that they are exactly the same as well. They just give more info here. And also just note that the 2024 paper has this line CE, where this one does not have that line CE. Okay, so this has 4 questions, and up to the first 4 questions, it's also exactly the same. Okay, same thing all through. So we're just going to continue from this point. I'm going to input this explanation because it's still the same thing. We'll use the same diagram, but I'm just going to draw that line down, okay, perpendicular to the x-axis, and put that point E, and let's continue from 2.5. Okay, so here is the explanation for 2.1 all the way to 2.4. Please note that it's going to be called question 3, and you know it's 3.1 to 3.4, but it is these questions. Okay, so let's get into this. Question 3 says, in the diagram below, A is the point where we have -2 and -1, and then we have B, which is -3 and 4, and C, which is 1 and 5, and then also give us D. So D is 5 and Y, okay? And the first question is to find the length of AC in simplified surd form. Okay, so AC. So when we have the coordinates, we can just use the distance formula. Distance equals the square root of x2 minus x1 all squared plus y2 minus y1 all squared. So AC equals, and we can take this as the second point, so point number 2, and this is point number 1. So x2 is 1, that's 1 minus x1, which is -2, and then all squared, plus y2 minus y1, that's 5, minus -1, all squared. And just go ahead and punch that into your calculator, and let's get our answer. And our final answer is 3 square root 5 units. Okay, and that is it for this question. Moving on to the next question. Question 3.2 says determine the gradient of BC. So use the gradient formula. Okay, so this is y2 minus y1 over x2 minus x1. Okay, so the gradient of BC using B and C, we have these 2 points. Okay, so that is y2 minus y1, 5 minus 4, 5 minus 4, all over, and we have 1 minus -3. So 1 minus -3, you can see 5 minus 4 is 1, and that's just going to be 4. So our answer is 1 over 4. That's the gradient of BC. Moving on to the next question. Then question 3.3 says, determine the value of y if B, C, and D are collinear. So they're collinear, meaning they lie on the same line. So if they lie on the same line, then this means that the gradient would be exactly the same, because this is one line. So the slope is exactly the same all through. So how we can find y, it's just one missing value. We can find it using, see, we can say, look, we know the gradient of BC. Okay, so we can go ahead and try to find the gradient of, let's say, CD or even BD. Okay, so in other words, we're just saying the gradient of BC is exactly the same as the gradient of, I'm just going to go with CD. Okay, because they lie on the same line. Okay, and then I'll just put the points down. Okay, so the gradient of BC, we already found that, okay, to be 1 over 4. If we rewrite this as 1 over 4, this is equal to, and it's equal to the gradient of CD, so this is C and D. Well, I'm just going to go with this being y2. So y minus 5 over 5 minus 1. So this is 1 over 4 is equal to, and this is just y minus 5, and then that just becomes 4. Okay, the denominators are exactly the same, so you can just equate the numerators. This is because you can get rid of the 4 simply by multiplying both hand sides of this equation by 4, and so you see 4 cancels in the denominator. So all we're saying is y minus 5 is equal to 1, and so therefore y is equal to 1 plus 5, which is 6. And that is our answer. The value of y is simply 6. Moving on to the next question. Question 3.4 says, if H is a new point such that AH is perpendicular to BC, determine the equation of AH. Okay, so with these questions, you actually don't need to sketch anything. You just have to take notes of everything they're saying. So H is a new point, no problem. AH is perpendicular to BC. That's where you need to start taking notes. So AH is perpendicular to BC, which means that if you take the gradient of AH and you multiply it by the gradient of BC, they will give you -1 because they are perpendicular lines. And so with this info, we need to determine the equation of AH. Well, the thing about AH is we don't know what H is, but we do know what A is. So it means that it goes from A to H. But we know that A, using our diagram, okay, is -2 and -1. So that is -2 and -1, and we're just going to do this. So what is the gradient of BC? Did we at any point find this? Yes, we did. It's 1/4. So to find this, we say the gradient of AH multiplied by 1/4 is equal to -1. And so to finally find this, you can divide both hand sides by 1/4 since it was multiplying to AH, or you can multiply both hand sides by 4. And then that way it will get rid of that 4 as a denominator. So we just have M of AH, okay, the gradient of AH equals, we multiply by 4 here, -4. Okay, we have the gradient and we have 1 point on the line. So we can find its equation. We can use y equals mx plus c, and I'll just go ahead and use that here. Y equals mx plus c. We can see our gradient is -4, so x plus c. And then to find c, just substitute 1 point on the line, which is -2 and -1, okay, in place of x and y. So in place of y, we say -1 equals, and we have -4. And then in place of x, -2 plus c, and solve for c. Okay, remember that this is the equation we'll put it back into because we're just trying to find c. So -1, that becomes +8, but when you take it over, it becomes -8. So -1 minus 8 is -9. So c is simply equal to -9. And finally, y is equal to -4x minus 9. And that is our answer. Okay, so remember we're still working on this question. Okay, question 2, not 3. And this is just continued. So 2.5 and 2.6. Let's go. 2.5 says, calculate the coordinates of G, okay, if CBAG in that order is a parallelogram. So that's CBA, and so G would be somewhere here. Okay, so let me just go ahead and draw that out, and then we can think this through. Okay, so CBA, and then this would be G. Okay, so with this, how do we calculate the coordinates of G if this shape is a parallelogram? So if it's a parallelogram, there are some properties that you need to know. So we don't have to prove these properties. It just means that they are currently true for this particular shape. But we need to think about the best one to use to find G, seeing that this is a missing point, meaning x and y are both not here. Okay, we don't know the x and the y coordinate. So you could think about the fact that it would mean that if this is a parallelogram, it means that these lines are parallel. Okay, so those two are parallel, these two are parallel. And you know that if lines are parallel, then they share the same gradient. But the thing is, if I found the gradient of this line and I tried to find the gradient of this line's gradient is going to be in terms of x and y, meaning it will include x and y. And then how do you solve for that? Okay, because now you have one equation that has x and y. It's not two equations where you can solve for x and y separately. So I wouldn't go with that. Another thing I wouldn't go with would be to use the distance. So saying if this is a parallelogram, then the opposite sides are equal. I wouldn't go with that either because then you have to use the distance formula. And with the way the distance formula looks, how it says that the distance is equal to the square root of, x2 minus x1, all squared plus y2 minus y1, all squared. This would also form an equation because you'll know the distance of one side and you're saying that it's equal to the distance of that other side. But this one will be in terms of x and y. And then we will have the same problem again. So what we can do here is use this that we know about parallelograms. And that is about their diagonals. If this shape is indeed a parallelogram, what it means that its diagonals will really just bisect each other. Okay, so for the diagonals to bisect each other, it just means that this diagonal, okay, AC, is cutting this diagonal BG, meaning it cuts it in half, and then it makes this part equal to this part. And then it also means that BG is also bisecting AC, meaning this is equal to this. And so because of that, you see how this is equal to this. That means this center point here is the midpoint. And you know how that is equal to that. This is also the midpoint. So it means that they have a common midpoint. And that's what we're going to use, that the diagonals bisect each other, meaning they have a common midpoint. So the first thing is to find G, we can find the midpoint. And we can find the midpoint, though we don't have G like that, we do have A and C. So let's find the midpoint of AC first. Then we can use that midpoint to find the point G. Okay, so let's find the midpoint of AC. So we'll find that by saying x1 plus x2 over 2. You can just add like that. So we'll say negative 2 plus 1 over 2, and then negative 1 plus 5 over 2. So this is finally the midpoint of AC is simply, so that's going to be negative 1 over 2, negative 1 over 2, and then 5 minus 1 is 4. So 4 over 2 is 2. Okay, so negative half and 2. That's the midpoint. But because this is a parallelogram, it would mean that the diagonals bisect each other, meaning the midpoint of their diagonals are exactly the same. So the midpoint of AC is the same thing as the midpoint of BG. Okay, so because of that, let's go ahead and try to find the midpoint of BG. Okay, so the midpoint of BG would be found by saying x1 plus x2 over 2. I'll just start with this one being x1. So this is x plus negative 3. Okay, if you say x plus negative 3, it just becomes a minus 3. So minus 3 over 2. And then y1 plus y2 over 2. Okay, so that's y plus 4, y plus 4 over 2. And what we're saying is we know that the midpoint of BG is equal to the midpoint of AC. So that was negative 1 over 2 and 2. That this is exactly the same as the midpoint of BG. So this is the calculation for the midpoint of BG. And so because they are exactly the same, they stand for the same thing. This is just the calculation. This is the actual midpoint. We can go ahead and say that their x values are exactly the same and the y values are the same. So it means we are saying x minus 3 over 2 is equal to negative 1 over 2. Okay, x is equal to x and the y values are the same. So y plus 4 over 2 is equal to 2. And then finally solve for x. So here we need to get to this. The 2 is distracting us. We need to get rid of it. Because it's divided by 2, we multiply by 2, but on both sides because it's an equation. So x minus 3 equals, that 2 cancels and you're left with negative 1. Transpose the 3, you have a positive 3. So x is equal to 3 minus 1, which is 2. Okay, so we got that. And here we would get rid of this. Just multiply both hand sides by 2 to get rid of that 2. And so y plus 4 equals 4. And then transpose the 4. So that is y equals 4 minus 4, which is 0. And so you can see that that point G is finally just 2 and 0. And that is our answer. And that is it for this question. Moving on to the next question. Okay, question 2.6 says, calculate the area of CEOF. Okay, so I just had to bring this diagram from this actual paper back. So I was using 2023's paper. But I see that there is one difference here, and that is that here they added F. But F is only used in the last question. They didn't really use it in the previous questions. So what they want us to find the area of is CEOF. Okay, so going from C to E to O and F. Okay, so this shape, CEOF. As you can see, that is not a triangle. It's actually a trapezium. So do you see how you have this OF, right? That is a vertical line. That is the y-axis. It's part of the y-axis. It's on the y-axis, really. Okay. And then there's this line. And this is a line parallel to the y-axis. And we know it's parallel to the y-axis because it's perpendicular to the x-axis. So we have a trapezium here. Okay, so let's just remove these and highlight that shape. So it's a trapezium, and to find the area of a trapezium, this is how we work with it, regardless of what it looks like, as long as you have its perpendicular height. So it could look like that. It could also, I wonder if it will auto draw it. Let's see. It could also look like this. Okay, so no. Okay, so like this. So as long as you have a pair of parallel sides, this is a trapezium. So this could be a case where you've got your perpendicular height like that, okay, where this line is perpendicular to this, or you can just visibly see your perpendicular height. And to find the area of this, we would simply just say the top part, okay, plus the bottom part, and then divided by 2, and then multiply by that perpendicular height. And then that's the area of a trapezium. Okay, so here you can see that if you tilt your head so turn your head this way, you would see that this is the top part, that is the bottom part, and then this is the perpendicular height. OE is the perpendicular height. So let's look at the things we need to find. We need to find the length of OF, the length of CE, and then the length of OE. But of course, if you know E, then you know OE. So the only challenge here is to find F. Okay. And from the previous questions, there's nothing that really, I don't think we ever needed to find the gradient of that. We found the midpoint of AC, okay, and, BG, those diagonals. But then, we don't have that as a gradient. So we need to find F first. Okay, so find F, find E, and then we would find this. Okay, let's find the simple thing first, E. E, as you can see, this is a line that is perpendicular to the x-axis. So it means that they are sharing the same x value. So this is 1, and because it's on the x-axis, the y value is 0. So we know that E, first of all, is 1 and 0. Okay, let's find F. So to find F, let's use AC. We've got 2 points on this line, and F is specifically on the y-axis. So it's the y-intercept of this. So I'm going to put the points A and C down. Okay, and let's find the gradient. So we can find the gradient of this line. The gradient of AC is equal to y2 minus y1. So -1 minus 5, and just be consistent. If you say top minus bottom, also continue with top minus bottom. So over -2 minus 1. So that's going to be -6, that's -3. When they divide, they become +2. So, okay, that is the gradient of AC, and we can find the equation of this line. So you can use y equals mx plus c, but I'm just going to use this. Y minus y1 equals our gradient times x minus x1. And so this is y minus, and this is x1 and y1. I'll just take this point because it looks easier. So minus, and we have 5 is equal to 2, and then multiply by x minus x1, which is 1. And so this is simply, well, I don't have to actually put this in standard form. I can just go ahead and find the y-intercept straight away. So to find the y-intercept, make x equal to 0. So y minus 5 is equal to 2 times 0 minus 1. And then solve for y. So y is equal to, just take everything else over. 0 minus 1 is -1, times 2 is -2. So we have -2, and this comes over to become a +5, which is 5 minus 2, and that is 3. So there we go. The y-intercept, okay, F, is 0 and 3. And that's all we need. So this is 3, and now we can find the top and the bottom and the height. Okay, so the perpendicular height, you can see that is 1 unit because you went from the center and then 1 unit to the right to get to this point, 1 and 0. So we know that OE is equal to 1 unit. Let's find OF, and then from the center, 3 units up, we get to F. So OF is 3 units. OF equals 3 units. And then lastly, B. So this is also an easy one to find because it lies on a vertical line, a line perpendicular to the x-axis. So to find the distance of this line, all you just need to say is, what is its y value here? Okay, that is 5. What is the y value here? That is 0. So this EC is simply 5 units. Okay, from 0 as a y value to 5 as the y value there. Okay, so EC or CE is 5 units. CE equals 5 units, and we have everything we need now. And so the area of this trapezium, and they called it CEOF. So CEOF is simply equal to, we'll say the top plus the bottom, we'll say 3 plus 5, okay, over 2. So 3 plus 5 over 2 multiplied by the height. Let's actually just put, because it just looks so empty, let's actually just put these. So we're just saying OF plus CE. Okay, so OF plus CE over 2, and then multiply by that perpendicular height of OE. So this is 3 plus 5 over 2 multiplied by 1. So 3 plus 5 is already 8. 8 divided by 2 is 4. Times 1 is 4. So this is 4. And they didn't say it's centimeters or anything. We can see it's just units. So 4 square units. So 4 units squared. And that is our answer. And that is the area of chord CEOF, which is a trapezium. And that is it for question 2. Question 3 says, Okay, if cos 23 degrees is equal to the square root of 1 minus g squared, express the following in terms of g. Okay, so with these, you can clearly see that we need a trig diagram. Okay, so to find each of these. So let's go ahead and start with 3.1. Okay, so with our diagram, this is a diagram, but they just said cos 23 degrees and they told us the value of cos 23 degrees. So this means that if you measure, okay, from the x-axis from 0 degrees, 23 degrees, and we're going to have a line here, that if you find cos adjacent over hypotenuse, it gives you this, the square root of 1 minus g squared. So this is 23 degrees. And so we'll draw a line down perpendicular to the x-axis. Okay, so this is our x and our y-axis. And now we can go ahead and find out what this is. So remember from SOHCAHTOA, okay, the directions for cos is adjacent over hypotenuse. So adjacent over hypotenuse, which means that this is your adjacent side. And so what would that mean about the hypotenuse? Well, every value naturally has a natural denominator of 1. Okay, so the hypotenuse is 1. So we know hypotenuse is 1, and the adjacent side, so the side next to the angle, is the square root of 1 minus g squared. So that's the opposite. This is the adjacent. This is square root 1 minus g squared, meaning for us to find any trig ratio they ask for, we still need this opposite side. So let's find that. Because we have a right angle triangle, we can use Pythagoras. So the opposite side, you see that this represents a y value. Okay, so it's that amount of units up. So we'll call it y squared is equal to, and it's going to be the hypotenuse squared minus the other shorter side squared. So that is the square root of 1 minus g squared all squared. So y squared is equal to 1 minus, this would break open, okay, but you still have two terms, so protect with brackets. So it's 1 minus g squared. So y squared is equal to 1 minus 1 plus g squared. And so we can see that y squared is just equal to g squared, square root both hand sides. Of course, we consider the positive and the negative solution, but you can clearly see where this y value is on the positive part of the y-axis. So that is just equal to g. So the opposite side is g. And now we can find sine 23 degrees. Okay, so this is 23 degrees, which is going to say sine from SOHCAHTOA. We know that sine is opposite over hypotenuse. So the opposite over the hypotenuse is simply g over 1, which is just g. And that is our answer. Moving on to the next question. The next question, we need to find the value of tan 113 degrees. Okay, so this is an obtuse angle. We can reduce it using our reduction diagram. So this is tan 180 degrees minus, it actually just looks like it's going to be cofunctions. We could just do this. So here's the thing. I'm seeing that if you said 90 degrees, right, plus 23 degrees, that would give you 113 degrees. Okay, because they add up to 113 degrees, but this is 90 degrees, we could use cofunctions here. So to use cofunctions, we would have to change this tan into sine over cos. So this is going to be sine 113 degrees over cos 113 degrees. Okay, there are different ways of doing this, but I'm just trying to do it this way. So this is equal to, and so then change that. You see, we know that sine 90 degrees plus theta, okay, because this is an angle greater than 90 degrees. So that's 90 degrees plus theta. This is equal to cos theta. And you know that cos 90 degrees plus theta, that is equal to negative sine theta. And so with this, you know that that can be separated into 90 degrees plus 23 degrees. And so this changes to cos 23 degrees. And this is over, okay, and you see that that's going to be cos 90 degrees plus 23 degrees, which we can see from cofunctions will change to negative sine theta. So negative sine 23 degrees. So negative sine 23 degrees. So this is just changing it using its identity and then using cofunctions immediately. Okay, so now cos 23 degrees. I think we had cos, okay, yeah, we did. So that was square root 1 minus g squared. So we know that that is square root 1 minus g squared. And negative sine 23 degrees. Sine 23 degrees is g. So this is minus g. And this is our answer. Okay. Okay, so this is an alternative way to the way they would naturally do it, because they'll probably reduce that angle first and then change it. But then I thought, we can already see this 23 degrees, so you can just use cofunctions as well. Okay, moving on to the next question. Question 3.3 says we need to find the value of sine negative 653 degrees. So whenever your angle is negative, all you need to do is add 360 degrees until it becomes positive, because it just has to do with the way it was measured. Okay, so you could have measured negative 633 degrees by starting here, and instead of going anti-clockwise the way angles are normally measured, okay, because you see your angles increase like that, 90 degrees, 180 degrees, 270, it's measured anti-clockwise, so it probably went around maybe almost twice. Okay, it wouldn't be a full twice, but then it lands somewhere, and then with that, to bring it back so that you can understand the value of the angle, you're just going to add 360 degrees. So plus 360 degrees, which is a full revolution, and then plus 360 degrees again. Okay, so add 360 degrees. Clearly, we need to add it like twice to get it to become positive. Okay, so if you take negative 653 degrees, you say plus 360, you see it's still negative. So again, add 360 degrees. You're just moving in a circle. And so this is really just sine 67 degrees. Okay, it's just 67 degrees. And let's go ahead and work with this. So 67 degrees and 23 degrees. Try to add them first, because we're just trying to compare everything to 23 degrees. If you add these, you see that's 80 and 10, so 90 degrees. So these are complementary angles. You can choose to, in your diagram, actually just find this. That will be the 67 degrees. Okay, 180 degrees minus 90 degrees minus 23 degrees would give you the 67 degrees, or we could just straight away use cofunctions. So if you say sine 90 degrees minus theta, this is equal to cos theta. So sine 90 degrees minus what exactly would give you 67 degrees? That would be minus 23 degrees. And so this is equal to, we can just go ahead and use cofunctions. You see how we had that? And it's equal to cos theta. So this is equal to cos 23 degrees. And now we can find that. So we know that cos 23 degrees was just root 1 minus g squared. We saw that initially. You can also use it like this, adjacent over hypotenuse. Okay, so square root of 1 minus g squared is our answer. And that is it for this question. And that is it for question 3. Question 4.1 says, simplify the following without using a calculator. And 4.1.1 gives us this. And I'm just going to rewrite this expression. Okay, so do you see that first we have this cos 390 degrees. 390 degrees is an angle that is greater than 360 degrees. So what you can do is, when it is greater than 360 degrees, subtract 360 degrees from it. So 390 minus 360 is 30 degrees. Okay, so 30 degrees. And then this is over cos negative 30 degrees. So with this, the angle is negative. When the angle is negative, you can simply add 360 degrees to it. If you do that, immediately it will just become cos positive 360 degrees, which was added, and then you still have negative 30 degrees. You can simply just see this as cos 360 degrees minus theta and then reduce it. Okay, using our reduction diagram, you know that this will reduce to positive cos theta. Okay, so positive cos, and how theta here is 30 degrees. So this is just cos 30 degrees. Okay, so you see that they're exactly the same. They're just going to simplify to 1. And then minus, now you know that tan 360 degrees minus x. Okay, 360 degrees minus theta, that is in cos's quadrant where tan is negative. So we have negative tan x over here. And then it is multiplied by, and here we have cos 180 degrees plus x. That is in tan's quadrant. So that gets reduced to negative cos x. And here we have cos x minus 90 degrees. You notice something about this? The angle is negative. Okay. Naturally, when the angle is negative, we can add 360 degrees. But with this is a 90 degrees, so they clearly use cofunctions here. Okay, so with cofunctions, there's actually a quicker way to do this. Instead of just adding 360 degrees, you can do this. So you see cos x minus 90 degrees. What we're going to do is take out a negative in this bracket. Okay, so we still have cos. Now in the bracket, we're removing a negative as a common factor, really -1. And you open a bracket, and here, what is left in the x if you take out -1 as a common factor? Just say x divided by -1 is negative x, but I'll put that x over here, negative x. And then negative 90 degrees divided by -1 is positive 90 degrees, right? And so this is what we have. So ultimately what we're saying is our angle is negative. Okay, there's a negative in front of it. And the rule is when your angle is negative, just add 360 degrees. So this is cos 360 degrees, and then you still have your minus 90 degrees minus x. So you can just see this as cos 360 degrees minus an angle. So let's say minus a. So in the same way this simplifies to cos a, okay, you can just see a as a replacement for this 90 degrees minus x. So that's the same way this would just end up being equal to positive cos of the angle that you have there. See, so that's a, and we just say 90 degrees minus x. Okay, so that's a way to simplify that. So with that, I can just, you don't really have to show all those steps because it's really co-functions, but the angle is negative. Okay, so it's just negative. If you wanted to still show a step, you can just show that, okay, I took this cos, okay, and I took out a negative from that. And so it just became positive 90 degrees minus x. And then in the next line, just show what it simplifies to, okay, because that would be something you just think about and reduce in your head. Okay, so we've got these two are exactly the same. They divide and just become 1, okay? So they cancel and cancel, they become 1. And now let's just look at this. We have to look at this entire expression and see how many terms we have. In algebra, terms are separated by plus and minus signs. So here is the minus sign, and then you see all of these have just been multiplied. Okay, that's been multiplied all through. So this means this is one term, and then this is a whole nother term. So if all of them are multiplying, let's look at their negatives. Negative times negative is positive, then times the negative is a negative. Okay, and we know this one becomes positive, but regardless, we would just have, ultimately, they become negative. Okay, so we're not going to look at the signs of these three first ones. Okay, these three negatives. Okay, so now look at tan x. We could change that to its identity, which is sine x over cos x. And then this is being multiplied by, remember that negative is already here. We multiplied all through. So multiply by cos x. And then multiply by this, which we know simplifies to cos 90 degrees minus x, which, you know, you can use co-functions on that. Okay, so I'll just change it to cos 90 degrees minus x, and then I don't need all of that. And now we're just, you know, cleaning this up. So this is equal to, we have 1 minus, and all through here, this is just one single term. You see that cos x and cos x would cancel, and so you're left with minus sine x, and this is being multiplied to this, which using co-functions ends up becoming sine x. Okay, so cos 90 degrees minus x. The only one that becomes negative is that cos 90 degrees plus x. That becomes negative sine x. Okay, so this is what we have. And so our final answer is 1 minus sine x times sine x is sine squared x. Okay, we need to simplify to a, you know, single trig ratio. So 1 minus sine squared x. Do you remember that sine squared x plus cos squared x is equal to 1. Okay, so if you wanted sine squared x to come over, you just take that over, and you would see that this would become 1 minus sine squared x. And so this is equal to cos squared x. So our final answer is just cos squared x, and that is our answer. Okay, and that is it for that question, which was a total of 8 marks. Moving on to the next question. Okay, 4.1.2, we have to simplify this, and this is for 4 marks. So this is equal to, you can just start straight off. You see that sine 120 degrees, okay, you can reduce this, and you can see that 120 degrees is an angle greater than 90 degrees, but less than 180 degrees. So it's going to use this reduction. So 180 degrees minus what gives you 120 degrees, that is minus 60 degrees, okay. So using this, you can see that it's going to just reduce to positive because we're using sine here. So it's positive sine 60 degrees. Okay, that was the angle we were subtracting by. multiply by, and then we have tan 330 degrees, which is an angle that is greater than 270 but less than 360. So we'll use that reduction. So this is tan 360 degrees minus what gives you 330, and that is minus 30 degrees. Okay, so that is just going to be, you can see that this reduction is in cos's quadrant, so it's going to end up just being negative tan 30 degrees. So this is minus tan 30 degrees. We can just say minus tan 30 degrees, and then all over, and they say cos 240 degrees, which is an angle greater than 180 but less than 270 degrees. So we'll use tan's reduction. It's cos 180 degrees plus what gives you 240 degrees. That is plus 60 degrees. Okay, so it's not in cos's quadrant, so it's just going to end up being negative cos 60 degrees. And you can see that we are using special angles all through. So you can either use the triangle or your calculator, but they did say without the use of a calculator. So let's just actually stick with that. So without the use of a calculator, I'll just use this rule called the OHA rule. So OHA, opposite, hypotenuse, adjacent. And then for your angles, we have 30 degrees, 60 degrees, and 45 degrees. Then you're just going to say 1, 2, 3, 3, 2, 1, and 1, 2, 1. And then in each row, square root the biggest number. So here we square root 3, here square root 3, and here square root 2. Now you're going to use this with SOHCAHTOA. So for sine, cos, and tan, okay, so you know the directions. And so with that sine 60 degrees, this is what we say. Sine 60 degrees, right, we'll go to the 60 degree row, and we're looking for sine, so that's opposite over hypotenuse. So in 60 degrees, take the opposite over the hypotenuse, so we know that this is actually root 3 over 2. Multiply by, now I can see this is negative and that's negative, so the negatives would cancel. Okay, and then tan 30 degrees. So go to 30 degrees and then look for tan, so opposite over adjacent. So that is going to be 1 over root 3. So 1 over root 3. And then this goes all over cos 60 degrees. So, okay, and then we have cos 60 degrees. So go to 60 degrees and we are going to go for the adjacent over the hypotenuse. So adjacent over hypotenuse is 1 over 2. That's 1 over 2, so just 1 over 2. And now we can just simplify this. Okay, so do you see that in the numerator, right? Root 3 and root 3, because they're exactly the same, we can cancel them diagonally. And the reason why is because even if you were multiplying their numerators, numerator times numerator, you have root 3 there. And then denominators multiply, you have 2 root 3. They would cancel like that. Okay, so whenever you see you're multiplying and you can see common factors diagonally, just cancel them out straight away. So this is actually going to be, numerator is just 1 there. So it's 1 over 2 divided by 1 over 2. And you can see that anything divided by the same thing is just equal to 1. And that is our answer. Okay, moving on to the next question. Question 4.2 says, prove the following identity. So let me just rewrite this identity. Okay, remember we're using the left-hand side because, we have something to work with here and we can find how this is equal to this right-hand side of 1. Okay, so here we go. And let's go ahead and start simplifying. So this is equal to, this is a fraction alone. And you see that we have tan squared x. So we can change that to its identity. So we have cos x. So since tan x is equal to sine x over cos x, then tan squared x is equal to sine squared x over cos squared x. Okay, and this goes all over 1 over. Now, I want to actually just rewrite that, but I can see that overall, we just need to add all of these, eventually get them added, and then they will be equal to 1. So I'm going to get adding with these ones. You see, in the denominator, you've got 1 over cos x plus 1. To add fractions or to add values, if you have a fraction, the denominators need to be the same. So you can rewrite 1 as, so that it has the denominator of cos x, you can write it as cos x over cos x. Okay, so you see how that's just going to be together. So we have plus, and we shouldn't forget this, cos x here. And then it's equal to, now over here, what happens is this cos x is going to cancel diagonally. Whatever is common diagonally and we're multiplying will cancel. So it cancels with that cos x. So we still have a sine squared x in the numerator and a cos x in the denominator. So sine squared x over cos x, but then in this denominator, what's going to happen is we have 1 plus cos x, okay, and then over cos x. Here's how we can rewrite it. You can just divide. You're saying divided by. So that's that divided by. And we're just going to call it 1 plus cos x all over cos x. Okay. And then, so this is together, and then this is plus cos x. We don't even need brackets. We know, using BODMAS that you're supposed to start with a division, okay, before addition. Or really just looking at the terms, okay, because these are dividing. This is one term, and there's your plus sign separating, and then that's your other term. Okay, so this is equal to, we can use tip and times here. So leave the fraction, the first one, exactly the same, and you are going to tip the second fraction, meaning swap its numerator and the denominator, and then that division, we're going to change it to a multiplication. Then we still have plus cos x, and this is equal to, and now what happens here is the cos x will cancel, and you are left with, in the numerator, all we're left with is sine squared x. In the denominator, all we are left with is 1 plus cos x. And then plus cos x, and this is equal to. Okay, so you see that here, all we have to do is make the denominators the same. So if we made the denominator, clearly, to make the denominator the same, this is just a 1. So everything needs to become 1 plus cos x. So here, this is already, it has a denominator of 1 plus cos x, so it stays exactly the same. But how would you get this one to have this denominator? You'd multiply the denominator and the numerator by 1 plus cos x. Okay, so you're multiplying it by something with two terms, so use brackets. When you multiply in, you're going to get a cos x and a cos squared x. I'm just going to write the cos squared x first because you can see that's where the 1 is going to be formed. And then the plus cos x. Okay, so this is where everything happens. So sine squared x plus cos squared x is the identity for 1, and then that's plus cos x, and the denominator is just 1 plus cos x. And so you can see same thing divided by the same thing is equal to 1, which is indeed the right hand side. And there we go, we have proven this identity. Moving on to the next question. Question 4.3 says, given the expression cos 2x times tan x over sine squared x, determine the value or values of x in the interval where x is an element of 0 degrees all the way to 180 degrees, for which the expression will be undefined. Okay, now with this, you know that an expression is undefined when its denominator is equal to 0. Okay, so when that is equal to 0, it's undefined. But with this one, we need to be a little careful. And the reason why is because they've introduced a special graph that can also be undefined regardless of, you physically seeing the denominator being equal to 0. And that is the tan graph. Okay, the tan graph has asymptotes. So it means that at those x values, it's undefined. So we need to consider that as well. Okay, so we can actually just show that this is where the denominator, okay, sine squared x is equal to 0. Okay, of course, within that interval, okay, where x is an element of 0 degrees all the way to 180 degrees. This is me just stating these things. At the end of the day, you just need to tell them the values of x. Okay, and they'll give you marks for that. And then I'm also just saying it's specifically where the tan graph is undefined. So I'm just saying this so that I know what I'm looking for. Okay. Okay, let's start with the sine graph, which is much simple to find. You can find out what sine x is by square rooting both hand sides. And you know how you say, I'll consider the positive and negative solution. Yeah, 0 is neutral. Okay, it's neither positive nor negative, so it wouldn't matter. This is just sine x is equal to 0. And now we can think about places where the sine graph has a y value of 0, because this is sine x, meaning y equals sine x. So now they're saying when the y value is equal to 0, what is the x value? So we need to find out the x values where the y value is 0 on the sine graph. With this one, I will not use that cost. Okay, where I say take the first and this quadrant. No, I'm not going to use that. I'm going to actually use the sine graph so you can see where exactly this is. So if our denominator is equal to 0, okay, where the sine graph is equal to 0, look at the sine graph. The sine graph does this, goes up, down, and then back up again. It reaches the highest of 1 and lowest of -1. And these are the y values, okay? So these are y values. Where is the sine graph? Where does it have a y value of 0 within this interval? So do you see that at 0 degrees, this is a point 0 degrees and 0. So the y value here is 0. Where else does it have a y value of 0? You can clearly see that is where it intersects the x-axis. That is where we have a y value of 0. So that would be here. So what is that? Well, the sine graph goes like this. There's 0 degrees and 0. Then here, this is 90 degrees and 1, 180 degrees and 0, 270 degrees and -1, and then 360 degrees and 0. Okay, so for this interval specifically, that would be at 0 degrees and 180 degrees. Okay, so that is our answer for this part. We'll just tell them this is where x is equal to 0 degrees, okay, or x is equal to 180 degrees, and then we're done with that sine graph. Okay, let's look at the tan graph and then just point out where it's undefined. So with the tan graph, just also remember what the tan graph looks like for that interval. Okay, it is a tan graph, and you know that the tan graph repeats itself every 180 degrees. And this is what a full cycle of a tan graph looks like. So it starts here at 0 and 0, it goes up, and then it reaches an asymptote. And that is what we're looking for when it has an asymptote. Because if you try to substitute, and I will go ahead and when we get that answer, we'll substitute it back into that expression and you'll see what will happen. And then it goes like that. So this is 0 degrees. Then it hits its asymptote at 90 degrees. And then we have 180 degrees. And then this is one cycle of the tan graph. So this is tan x. And we can see that where it will be undefined is at 90 degrees. Okay, so there we go. This is where x is equal to 90 degrees. Now, if you take this expression on your calculator, okay, like that, and you actually substitute these values, you will see that they will be undefined. So when you try 0 degrees, okay, 0 and 0, and then the minute you put 0 there, see, indeterminate, so it's undefined. If you tried 180 degrees, you'd have a similar situation. So you see, it's still saying indeterminate because that denominator is 0. So 180, same thing. Try 90 degrees. Now 90 degrees, if I just put 90 degrees here and 90 degrees here, it looks okay. It's like, oh, it's 0. And then you're like, oh, but it's fine. But then once you make that equal to 90 degrees, then you see what happens, complex infinity. And so because of that, there's an asymptote, and that's the reason why it's still undefined at the end of the day. So our three solutions are x equals 0 degrees, x equals 180 degrees, or x equals 90 degrees. And that is our answer. Moving on to the next question. Question 4.4 says, solve for alpha and beta if, and they give us this. So they tell us that cos alpha plus beta is equal to -√2/2, okay? Specifically, where we have alpha plus beta is an element of 0 degrees all the way to 180 degrees, okay? So that is telling us about that reference angle. So we don't have to consider general solutions in this case. And then the second thing they tell us is this one, okay? So second equation they give us is cos alpha minus 2 beta, and this is equal to 1/2, okay? Where alpha minus 2 beta is an element of 0 degrees all the way to 180 degrees. Okay, so we don't really have to use general solutions here to solve for alpha and beta. What we have to do is just find that reference angle, and then we know that that reference angle is going to be an angle that is greater than 0 but less than 180 degrees. So just the normal way you would solve for trig equations if you were finding the general solution. But this time I'm not going to use plus k of anything because it's not necessary. They've already told us, okay, that, we're not just finding general solutions, there's specific solutions. Okay, so in this equation, let's go ahead and find that reference angle. So we do this by transposing. So there's two methods. There's the ones where you consider the table. I prefer using the table when we are working with general solutions. So in this case, I'm not going to use the table. I'm just going to go ahead and find the second function of -√2/2. And normally, okay, if you say shift cos √2/2, that will give you 45 degrees. So because it's negative, it's going to be on the other side. It's going to be 135 degrees, but you can just still check at the end of the day. So just say shift cos, and if you say -√2/2, we get 135 degrees. So I'm not going to consider the table. I'm taking it as negative, okay? So it is 135 degrees. The reference angle they are referring to is currently 135 degrees, and you can see it is an angle that is greater than 0 degrees, but less than 180 degrees. Okay, so naturally, when we're solving for this, once we find the reference angle, we can finally say whatever we had, okay, in front of cos, we're going to take that alpha plus beta, and then this is equal to positive or negative of our reference angle. So this is using a different method. Okay, fine. So let me just deal with this in a method that would probably be more familiar. Let's find the reference angle, and we find this by saying shift cos and then the absolute value of this. So we won't take the negative, we'll take the positive. You see that if you take the positive of that, it gives you 45 degrees. So this is 45 degrees. And then what you're going to have to consider is your table. So now we're going to look for our solutions specifically. So we're trying to solve for, or really just leave this as a subject as alpha plus beta, like with general solutions. And we're going to find all the places where cos is negative. Okay, so A, S, T, C, your cos diagram. Cos is negative in sine and tan's quadrant. So use those reductions. That's 180 degrees minus theta, 180 degrees plus theta, and you'll see that one of them will not work for this. Okay, so here's the thing. We say 180 degrees minus 45 degrees, you're going to get 135 degrees. But if you say 180 degrees plus 45 degrees, you're going to get 225 degrees, which is not within our interval. Okay, alpha plus beta is an element of 0 to 180 degrees, so we won't even consider that. We'll stop here. And that's the reason why I don't want to go through the general solutions path, because this is just a simultaneous equation. They just want you to solve for alpha and beta. Okay, so we would stop here and would say, okay, we have our answer there, and we'll just use this if necessary again. So this is what we have. So currently, alpha plus beta is just equal to 135 degrees. Okay, so this is our first equation. We'll probably have to make something a subject, but we'll see. So this is the first equation we have. Let's continue with this side. If you were given a trig equation cos alpha minus 2 beta is equal to half, you would need to find the reference angle first, just like we did here. So let's find that reference angle. We'll just say reference angle would be found by saying, in this case, there's no complication because it's positive, okay? A half is positive. So again, we're working with cos. Take cos over, becomes the second function of cos. If you say on your calculator, shift cos of a half, you can do that. You will get 60 degrees, okay? So it means that alpha minus 2 beta equals, now with your table, you'd say, where's cos positive? First and fourth quadrant, okay? So this is 60 degrees, but the other one is 360 degrees minus theta. So you would say alpha minus 2 beta is equal to 60 degrees, then plus k 360 degrees. Or alpha minus 2 beta is equal to 360 degrees minus your reference angle, which is 60 degrees. But then if you said 360 degrees minus 60 degrees, you're going to get 300 degrees. They told you that alpha minus 2 beta is an element of 0 degrees all the way to 180 degrees, so it's not this big. So we only consider the one in the first quadrant. This is why I prefer using the actual trig graphs to look at this. So you need to make sure you study your trig graphs and understand how to draw them, how to find the x values for certain y values, and so on. So this is simply equal to just 60 degrees, and we would take that. Okay, so this is our equation that we have here. Now, do you see in both equations how we have alpha and alpha on their own? Okay, there's no 2 in front of that or anything. So in both equations, what I would just do is make alpha the subject. So here I'll say alpha is finally equal to, we have 135 degrees on the right hand side, and I'm going to transpose beta, so minus beta. And so this is the equation I'm working with here. And then same thing here, but here we just have to take over that negative 2 beta. So alpha equals, and we still have 60 degrees, then becomes plus 2 beta. Okay, so there, alpha is our subject in both equations. And now, because alpha is the subject, this is a simultaneous equation. We're solving for alpha and beta. I'm just going to say, therefore, alpha is equal to alpha, okay, and equate. So, okay, I see 2 beta on this side, so I'm going to start with this equation. 60 degrees plus 2 beta equals, and we have 135 degrees minus beta, and then 2 beta, if you transpose, this becomes plus beta. So this is 3 beta equals, we have 135 degrees minus 60 degrees. It's 105 minus 30. Okay, so we have 75 degrees. And then divide both hand sides by 3 to finally get that beta is equal to 25 degrees. And then solve for alpha. Just take the easier looking equation. I'm just going to go with this one, right? Okay, so alpha is finally equal to 135 degrees minus beta, which is 25 degrees. And so you can see that alpha is simply equal to 110 degrees. So these are answers for alpha and beta like they asked for. And that is it for that question, and that is it for question 4. Question 5.1 says, in the diagram, O is the center of the circle, AB and AC are chords, and BO and CO have been drawn. So you can see that those are radii, okay? So from the center to the circumference. Use the diagram on the diagram sheet to prove the theorem which states that the angle subtended by an arc or chord at the center is equal to twice the angle subtended by the same arc or chord at the circumference. That is proof that angle BOC is twice the size of angle BAC. Okay, so to prove this theorem, we're just going to have to make one construction, and that is drawing a radius from O to A, or really just from A to O, and then extending it out to a point. So I'll extend it to a point and call that point P. And then this causes us to have two angles here now. So we've separated angle O into angle O1 and 2, and angle A into angle A1 and 2. And then just make sure to write down any constructions that you've made. Okay, so there we go. And now to prove this theorem, this is what we're going to do. We are going to use each of these triangles that we see here. So this is the first triangle. And do you notice that this triangle has an exterior angle, and that is angle O1. So the exterior angle of a triangle is always equal to the sum of the two opposite interior angles. So we know that angle O1 is equal to angle A1 plus angle B. Okay, so there we go. And our reason is because we have an exterior angle of a triangle. But here's what we also see in this triangle. Do you see that in this triangle has a radius from O to B and then from O to A. We know that the radius all around the circle, okay, all the radii, they're exactly the same. So they are equal in length. And so we can go ahead and tell them that first, and it will make two angles equal. So we can tell them that OA is equal to OB because these are equal radii. But here's the thing about this. Because these are equal, it means that the angles opposite these equal sides are also equal. So that means angle A1 is actually equal to angle B. So let's state that. Okay, and the reason for this is because we have angles opposite equal sides. Angles opposite equal sides are equal. Okay, and now we can update this equation that we had. So this means that angle O1 is finally equal to angle A1 plus, now in place of angle B, we can just say angle A1 because they are equal. Okay, angle B and angle A1 are equal. And we're focusing on angle A1 because you see that it's part of what they want us to prove. Okay, angle BAC is this angle. Okay, so that means that angle O1 is finally just equal to angle A1. Okay, so we have this part done. Now you're going to see a similar case happening on this part of the diagram, okay, in this triangle. Do you see that we have an exterior angle, angle O2? Then angle O2 is going to be equal to the sum of the two opposite interior angles, angle A2 and angle C. So we'll state that angle O2 equals angle A2 plus angle C, also because we have the exterior angle of a triangle over there. And then do you also see that in this diagram, OA and OC are radii, so they're equal. So because they're equal, we'll state that first, but then that would also mean that the angles opposite their equal sides are equal. Okay, so we know that AO or OA is equal to OC, and that's because we have equal radii. And so that means these angles, angle A2 and angle C, are also equal. Okay, and they're equal for the exact same reason that this was equal. And with this, we can now conclude. Okay, so we're going to update that equation. Angle O2 is finally equal to angle A2 plus, and in place of angle C, we're just going to say angle A2 again, since these are equal. So therefore, angle O2 is actually equal to angle A2. Okay, so we have that. Okay, so with that, do you see how what they asked us to prove was angle BOC is equal to 2BAC? So angle BOC is actually made up of the sum of angle O1 and angle O2. So if we add those two together, they give us that angle. So let's add them. We'll tell them we're saying angle O1 plus angle O2. But here's the thing. Angle O1 was finally equal to 2 angle A1, and angle O2 was finally equal to 2 angle A2. But we know that the sum of these angles, they make up this angle BOC. So we're going to just say this is therefore equal to angle BOC. And this is equal to, do you see how we have angle A1 and angle A2? Okay, so these, we need them to just be together. And so to get them together, do you see that we have a common factor of 2? So we can take out that common factor, and what are we left with? Angle A1 plus angle A2. And so therefore angle BOC is equal to 2. But we know that these two, when they're added up together, do you see the angle they give you? Angle BAC, that angle in the final proof. So that is BAC. Okay, and that is how we prove this theorem. So angle BOC is equal to twice the size of angle BAC. And moving on to the next question. Question 5.2 says, in the diagram below, DF is a diameter of the circle with center O. Chord EG intersects DF at H such that GH is equal to HE. And then they tell us that chords EF, GF, DE, and radius OE are drawn. Okay, and then lastly, they've given us an angle. So EGF is 55 degrees. And the first question, 5.2.1, says, write down the size of angle D and provide a reason. Okay, so angle D. What is angle D? Do you see how it's also at the circumference? And it is subtended by this chord EF. So which other angle at the circumference is also subtended by this chord? That is the angle G. Okay, so there we go. We can see it's actually equal to 55 degrees. So angle D equals angle G. Okay, and so therefore angle D is actually just equal to 55 degrees. And the reason is because we have angles in the same segment. So this is 55 degrees as well. And let's just put our reason down. Okay, you can also say angles at the circumference subtended by the same chord or arc are equal, but angles in the same segment is a much shorter reason. Okay, so that is it for that question. Moving on to the next question. Question 5.2.2 says, write down the size of angle O2 and provide a reason. Okay, so angle O2 is here at the center. So think about theorems that concern angles at the center. We know that the angle at the center is twice the size of the angle at the circumference as long as they are subtended by the same chord or arc. Okay, so chord EF subtends these two angles, this at the center and that at the circumference. So that means this is twice the size of that, meaning that's 55, that is 110 degrees. And let's just put our answer down. So angle O2 is therefore equal to 110 degrees, and we'll put our reason. Okay, and that is our answer. Moving on to the next question. Question 5.2.3 says, calculate given reasons the size of angle F2. Okay, so angle F2, that is over here. Okay, so do you see the situation that we have going on here with angle F2? So we have a radius, okay, from the center to the circumference, and then from the center to the circumference. And so we know that these radii, they are equal in length. Because of that, we have an isosceles triangle. Okay, so we have this angle, and so we have an isosceles triangle, meaning this angle over here is exactly equal to this angle, okay? Angles opposite equal sides are equal. So we're going to have to state those first. Let's start with the radii. We can tell them that OE is equal to OF first. Okay, so OE equals OF. And this is because we have equal radii, and then conclude the angles that are equal. So that means that angle F2 is equal to angle E, 3. Okay, angle F2 equals angle E3. You see that the focus will be on angle F2. And then we can also just put the reason there. That's because we have angles opposite equal sides. Okay, now with that, look at what we can just do. Because we have a triangle and we know that the angles in a triangle add up to 180 degrees, we're going to say 110 plus this angle plus that angle. So we can just put everything out first. So just go ahead and tell them that angle O2, okay, so angle O2 plus angle F2 plus angle E3, they're all angles that lie in a triangle, so they add up to 180 degrees. And our reason is because we have the sum of angles in a triangle. Okay, and now fill in. O2 was equal to 110 degrees. We're trying to find angle F2, so we leave this as angle F2. But we know that angle F2 and E3 are equal, so in place of E3, we're going to change that to F2 is equal to 180 degrees. Okay, and now we're just solving. So together they form 2 angle F2 is equal to, and if we say 180 degrees and transpose, that is minus 110 degrees, and that's going to give us 70 degrees. And then divide both hand sides of the equation by 2. Therefore, angle F2 is equal to 35 degrees. And that is our answer. And then just make sure to fill it in. So now we know that this over here is 35 degrees and so is this. That's also 35 degrees. And I'm going to leave those lines there. I know it's a radius, but yes, we can see it's equal. Okay, moving on to the next question. Question 5.2.4 says, prove with reasons that DE is a tangent to the circle passing through E, F, and H at E. Okay, so we need to prove that a line is a tangent. When you're trying to prove that, for example, a line is a tangent, you have to use theorems that relate to tangents. Okay, so there are a number of theorems that you can use. You can use the tan chord theorem if, the diagram supports it. With tan chord theorem, it's usually the one that you definitely must use because the other theorems that you can use apart from the tan chord theorem would be radius perpendicular to tangent. But you see, for that, you need to have a radius in the first place. I have no idea what I'm drawing here. Okay, tan chord theorem. The other one is radius perpendicular to tangent. But you see, if the diagram doesn't have a radius, a clear radius in that circle that they refer to, then it's useless to use that. Okay, there's also tangent drawn from the same point. Okay, so it's not only tan chord theorem, but it's mostly going to be the tan chord theorem whenever they tell you to prove that something is a tangent, okay, passing through a circle. So let's go ahead and see this. I'm just going to bring that diagram down. Okay, so what they're saying is that this circle that they're referring to, we need to prove first that DE is a tangent to the circle which passes through E, F, and H. Okay, so let me go ahead and draw a circle over there. Okay, so something like that. And what we're trying to do is prove that. So focus on the purple, okay? We're trying to prove that this is a tangent to this circle. So it passes through these 3 points, meaning it has the following chords. It has this chord, EH, okay, that is a chord in the circle we're referring to. And it has this chord, EF, and it definitely has this chord, HF. So clearly here we have to use the tan chord theorem because in this circle, this purple circle, you can see that there's no radius. Okay, we're not referring to this bigger circle. Focus only on the purple. So let's look at what we have in the purple circle. Do you see that we've got this angle 35 degrees, okay? And do you see that we also have this? So this is supposed to be a tangent. We're trying to prove that it's a tangent. For it to really be a tangent, then the angle between this supposed tangent, okay, and this chord should be equal to the angle at the circumference of the circle subtended by this chord. Okay, so in other words, what we are required to prove is that angle E1, that little angle over there, is actually equal to angle F2. Now, the good news is we already have angle F2. We know that it's 35 degrees. So all we need to find is the size of angle E1. And if E1 is eventually equal to 35 degrees, then it would be proving this theorem, meaning this is definitely a tangent. Okay, let's go. Okay, so with this, to find this angle, this is our focus, find angle E1. To find angle E1, do you see that all you would need is angle H3? So you could find angle H3 or angle H2. I think it would be easier to work with angle H2, okay? So with angle H2, why we could use that is because we could use this as the exterior angle of this triangle, okay? So we have this triangle over here. This is the exterior angle. If we find that, we can say it's equal to the sum of this plus this. So focus on finding angle H2. How do we find that? Angle H2 is in an interesting place. Do you see that we have GE, right? And they told us that GH is equal to HE. So we've got a line from the center of the circle to the midpoint of a chord. What do you know about that line? If a line runs from the center of a circle to the midpoint of a chord, that is perpendicular to the chord. Okay, so there we go. That's what we're going to use there. We can go ahead and tell them that we know that OH is perpendicular to GE. Okay, and put our reason down. Okay, I don't want to say line from center of the circle and just end there, because then, you're not actually saying the full theorem or really the main part. This is not the case of line from the center of the circle perpendicular to the chord. No, it's from the center of the circle to the midpoint of the chord. Okay, so it's therefore perpendicular to the chord. And so because of that, we know now that angle H2 is actually equal to 90 degrees. Okay, now remember that angle H2 is also the exterior angle of this triangle that we were looking at. So it means that the exterior angle H2 is equal to the sum of the two opposite interior angles. So we know that if you take angle E1 plus angle D, which is 55 degrees, that it would be equal to angle H2, which is 90 degrees. And this is because of the exterior angle of a triangle. And so finally solve for angle E1. Angle E1 is equal to 90 degrees minus 55 degrees, which would give us 35 degrees. And this is our answer. Okay, so we can see that angle E1 really is equal to 35 degrees. And so because we can see that angle E1 is equal to angle F2, this proves the theorem which states that the angle between a tangent and a chord is equal to the angle at the circumference subtended by that same chord. And so because that theorem is true, it means that this line DE really is a tangent. So we can finally conclude. Therefore, DE is a tangent. And the reason for it being a tangent is not because of the tan-chord theorem. If we say just the tan-chord theorem, it means that you're already assuming that this is a tangent. No, we are not assuming it's a tangent. We're saying the tan-chord theorem is true, therefore it is a tangent. So our reason here would be the converse of the tan-chord theorem. Okay, and that is our answer. And that is it for question 5. Question 6.1 says, in the diagram below, CD is a diameter and PC is a tangent to the circle at C. Chord DK is produced to P, and then PT intersects KC at Q. Okay, and then they gave us the size of angles. So we have CDP is equal to 40 degrees, DPT is equal to 25 degrees, and TQC is equal to 65 degrees. So calculate with reasons the size of the following angles, and 6.1.1 asks us for the size of angle C2. Okay, so straight away with angle C2, you see that it's the angle between a tangent and a chord. And so this angle is equal to the angle at the circumference subtended by the same chord. Okay, so there we go. We know that this is 40 degrees because of the tan-chord theorem. So angle C2 equals 40 degrees. And our reason is tan-chord theorem. And that is our answer for the first one. Moving on to the next question. Question 6.1.2 says find the size of angle K1. Okay, so angle K1 is over here. Okay, and straight away you see that it's the angle subtended by a diameter. Okay, the angle in a semicircle. So it's equal to 90 degrees. So you can just put that down. That's 90 degrees over there. So show them that angle K1 is equal to 90 degrees. And this is because we have an angle in a semicircle. Okay, and that is our answer for that. Moving on to the next question. Okay, the next question asks us for angle P1. Okay, that was scraped off a bit. Angle P1 is over here. How do we find the size of this angle? Okay, so the best thing to try to use here is, related to triangles. Okay, and the reason why is because it's just way out of, it's not even in the circle. So you can't even use theorems that, refer to a cyclic quad or angles in a circle. So let's just try to work with any triangles that we can see here. I see this triangle and I wanted to go with that at first glance, but then I just looked at T1. I'm like, I don't really know what T1 is right now. And I just feel like there would be an easier way to find this. So, okay, do you see this? So we have, an exterior angle here, and this is a triangle. Okay, so it means the exterior angle is equal to the sum of the two opposite interior angles. Do you see how they just keep using three really. They keep using three theorems, okay? The exterior angle of a triangle, and then they keep using the tan chord theorem. And another one they keep using is that angle at the center, okay? So just watch out for those. Okay, so we have this angle P1 plus 40 degrees would be equal to 65 degrees. So angle P1 plus 40 degrees equals 65 degrees, and this is because of the exterior angle of a triangle. So solve for angle P1. This is equal to 65 minus 40 is 25 degrees, and that is our answer. Moving on to the next question. Question 6.1.4 says, prove with reasons that TC equals QC. Okay, let's just put this down. It may be helpful. Okay, angle P1 equals 25 degrees. So we'll just put that down. P1 is equal to 25 degrees. Interesting. Okay, so that would mean that line actually bisects that. But okay, they say TC equals QC. So TC is over here and QC is over here. You should always celebrate when you see this type of situation. And here's why I say so. You see, when they're trying to ask you to prove two lines are equal, it's not always lines that are inside a triangle, okay? Sometimes it's two lines are equal, but then the lines look like this. Okay, so then you have to start thinking about cases when you've seen lines equal like this. Like if this was A, B, and C. So the things that could come out from this is maybe you had a triangle and you maybe had the midpoint theorem. Or maybe you had a circle, okay, a line going from the center of the circle. Okay, and maybe this was perpendicular. Then you'd be like, oh, okay, so that means these two are equal. Okay, but once they just do this, there's really only one route that they're taking. And if you notice that the two lines you have to prove are equal, lie in one single circle, it just means that you need to show them that the angles opposite those equal sides are equal. Basically show them that there's an isosceles triangle here. Okay, so you see, because this is 65 degrees, all we have to do is find angle T1. And if angle T1 is 65 degrees, then these angles are equal. Therefore, the sides opposite their equal angles are also equal. Okay, so you see that all we need to find is the size of angle T1. Okay, so looking at this triangle, we can just use this. So you see we have this larger triangle here, and we have angle P1, and you also see that we have this diameter. Okay, it's not a radius fine, but it's a diameter. And so we know that it passes the center of the circle. So wherever the radius is drawn from, we know that the radius is always perpendicular to a tangent at their point of contact. So this is 90 degrees, this is 25 degrees. We can use the sum of angles in a triangle to find angle T1. If we didn't want to go through that route, we could also do this. Do you see that? So focus on angle T1. And because we just have so much triangles here, we can actually just still focus on triangles. Do you see how angle T1 is actually the exterior angle of one of the triangles we have here? Angle T1 is equal to 40 degrees plus 25 degrees. Okay, that's a quicker way to find it. So we can just go ahead and say angle T1 is equal to 40 degrees plus 25 degrees. And that's because it is the exterior angle of a triangle. And so finally, angle T1 is actually equal to 65 degrees. Okay, so we know that this is also 65 degrees. And so because they're both 65 degrees, it means this is an isosceles triangle. Therefore, these lines opposite these equal angles are also equal. So let's finally conclude. TC is equal to QC. Okay, and instead of saying angles opposite equal sides are equal, this time we're not saying angles opposite equal sides, okay? Currently, the angles are already equal. So it means that we're saying the sides opposite the equal angles are equal. Okay, so it's a converse of that. So we'll say sides opposite equal angles are equal. Okay, so there we go. And so that's how we prove that. Moving on to the next question. Question 6.2 says, in the diagram below, O is the center of circle PTR. And then we have N is a point on the chord PR such that ON is perpendicular to PR. Okay. RS and PS are tangents to the circle at R and P respectively. And RS is 15 units, TS is 9 units, and then this angle RPS is 62 degrees. So 6.2.1 says calculate the size of angle NOR. Okay, angle NOR is this angle over here. So we need to find that angle. Okay, and this is for 5 marks. So for 5 marks, how would we find this angle? You can see it's just not a one-step process. Okay, so focus on this angle and how can we construct the way to find this? With this angle, we have triangles all over. Do you see that in this triangle, this little triangle over here, if we had this angle, we would know exactly what that angle is. So the goal is find this angle, because then you can just use the sum of angles in a triangle and then you'll find it. Or even the exterior angle, okay, because that will also be 90 degrees. So how do we find this angle over here? Well, let's look at where it is. We know that this is a tangent, right? And so we have a tangent, but O to R is a radius. So we know that the tangent and, or the radius and the tangent are perpendicular at the point of contact. But then that just finds this whole angle. It doesn't really find this. We need something that will help us to find this. So you see that if we know this is 90 degrees and we need this, then the next thing we need to find is this angle over here. Okay, so now with this angle, do you see this bigger triangle? We have tangents, okay, tangents drawn from the same point are equal. So that means PS is equal to RS. And so we have an isosceles triangle here, meaning these angles are equal. Okay, so there we go. You can see the steps that we can take to find this. So first, find this angle. So let's go ahead and state that. So we know that PS is equal to RS because we have tangents drawn from the same point. Okay, and so now that these tangents are equal, we can go ahead and say now that angle P, or that angle RPS, is equal to this angle. So let's call this angle SRP. Okay, so angle SRP is therefore equal to angle RPS. Okay, so angle SRP is equal to 62 degrees. Okay, so we've put our reason, and so we know that. Okay, so we know this is 62 degrees. And again, to find this angle, we can see that this radius is perpendicular to the tangent. So we can just go ahead and say, to find that angle, just say 90 degrees minus this 62 degrees. Okay, so start by stating OR is perpendicular to RS. So OR is perpendicular to RS. Okay, so that means this angle ORS is 90 degrees. Okay, therefore angle ORS equals 90 degrees. And so the reason for this is because the radius is perpendicular to the tangent at the point of contact. Okay, so now that they are there, we can just find this little angle. So that is 90 degrees minus 62 degrees. That gives us this angle ORN. Okay, so angle ORN is finally found by saying 90 degrees minus 62 degrees. And we'll put our reason. Okay, and that was our reason for it. So this is actually equal to 28 degrees. Okay, so now that we have this little angle and it is 28 degrees, then it means that to find this angle we're trying to find, NOR, we just use the sum of angles in a triangle. So to finally find angle NOR, this is equal to 180 degrees minus that 90 degrees minus the 28 degrees. Okay, so minus that. And so first put your reason. Okay, so finally NOR is equal to 90 minus 28 is 62 degrees. And that is our answer. Okay, so that is it for that question. Makes sense why it's 5 marks. And so we have that as 62 degrees. And that is our answer. Finally, moving on to the next question. Question 6.2.2 says, calculate the length of the radius of the circle. And this is for 4 marks. Okay, so the radius of the circle. I don't really think we need angles here. But okay, let's just try to focus on the lines that we see. So the radius of the circle, we've got some right angle triangles here. So, we could use Pythagoras, but let's just see how. They told us that TS is 9 units. So T to S. Okay, so we've got this right angle triangle here, but I can see that this is not that useful to find the radius because the radius goes from the center to the circumference. But look at the triangle we can use. We could use this triangle because we've got two things that can really be expressed in the exact same way. So you see, this is the radius. Okay, we can just call it R. We could also just call that R as well. And we know that from T to S is 9 units. And then we also know this side. So we're basically just using this triangle. Okay, and I'm just going to say, let the radius be R. And then so from O to T, I will also call that R. Okay, so it will form an equation which will be in terms of R, and then we can solve for R. Okay, I'm just going to take this down as well. Okay, so we can just go ahead and start by saying let OR equal R. So wherever you see OR, we're going to call it R. But here's the thing. OR is a radius, and so is OT. And so because of that, they are all going to be called R. So this is because we have equal radii. Okay, and so now that those are equal, we can just use Pythagoras here. So with Pythagoras, what we can say is we are using this bigger triangle. Here's the hypotenuse, okay? And then these are the smaller sides. So you know that the shorter side, so R squared, that's OR. Okay, let's actually just name it. So OR squared plus RS squared would be equal to OS squared. Okay, Pythagoras. And we'll just put our reason. This is because of the theorem of Pythagoras. Okay, and now OR is R. So that's just R squared. Plus RS is 15. So that's 15 squared. And then OS is actually made up of R plus 9 units. So that's R plus 9 all squared. And all we are doing is solving for R in this equation. Okay, so R squared and then 15 squared is 225 is equal to, and here we need to square that. So square the first term, that's R squared. Square the last term, it's positive 81. First term times second term is 9R. Then just double this. So multiply by 2, which is positive 18R. Okay, so this is what we have. And you can see now the R squared and the R squared will cancel because if you take that over, it becomes negative R squared. So it will cancel. So they're gone. And all we have is this 18R here. So let's leave it on the right-hand side and take that 81 over. So 225 minus 81. Okay, that's 144. And we can just go ahead and divide both hand sides of the equation by 18 to get rid of that 18. Okay, and so that gives us 8, meaning R is therefore simply equal to 8 units. And that is the radius. So we can finally conclude the radius is 8 units. Okay, so the radius is 8 units in length. And that is it for question 6. Question 7 says in the diagram, O is the center of the circle and PVR is a tangent to the circle at V. Okay. T is a point on the chord SU such that ST is equal to TU and then US extended meets PV at R. And then they just show us these, which is OV, so OV, OR, OS, and OT are drawn. Okay, so the first question, 7.1 says, prove that VOTR is a cyclic quadrilateral. Let's highlight VOTR. Okay, so VOTR is a cyclic quadrilateral. So there are 3 ways to prove that a shape is a cyclic quadrilateral. And here they are. There are 3 ways, or really theorems, that we can use to prove that a quad is cyclic. Okay, the first way we prove that a shape is a cyclic quad is if we see that the exterior angle of this quad is equal to the opposite interior angle, then it means that this is a cyclic quad. The second way is if the opposite angles of the quad, they add up to 180 degrees, then this is a cyclic quad. The third way to prove this is if you notice that the angles in the same segment, okay, so the angles at the circumference subtended by the same quarter arc, that they are equal, then this is a cyclic quad. These are all theorems that refer to cyclic quads. They are specifically true if you are given a cyclic quad. Okay, but with the way this shape looks and just the way it's constructed, you see how we don't have lines going across, so I'm not really going to focus on the angles in the same segment theorem. Also, I also see that I don't really have actual angles. Well, technically, we don't have physical angles yet, but we can probably find. But here's what we can go with. We can go with the exterior angle of a cyclic quad. You know that the exterior angle of a cyclic quad is equal to the opposite interior angle. Okay, so that would mean that, well, you can find it like that, or even like this. Okay, it'll still be fine. But with this, you see what's going on here. You've got from the center to the circumference, that's the radius. Okay, and this is the tangent. We know that the tangent and the radius are perpendicular at their point of contact. And then over here, do you see that this is also a radius? This is a chord, but they told us that ST is equal to TU, meaning this is the theorem which states that the line drawn from the center of the circle to the midpoint of the chord. What is that line? That line is perpendicular to the chord. So that would also be 90 degrees. Okay, so there we go. The exterior angle actually is equal to the opposite interior angle. And now we just have to state it for them step by step. So let's go ahead and start with this one. So we tell them that OV is actually perpendicular to PR. So OV is perpendicular to PR, and the reason why is because we have the tangent perpendicular to the radius at the point of contact. So therefore, that means that this angle OVP is equal to 90 degrees. So OVP is equal to 90 degrees. Okay. And then we can also see this case here. OT is perpendicular to, let's say, SU. Okay, so OT perpendicular to SU. And that's because we have a line from the center of the circle to the midpoint of a chord. Okay, and there we go. We can just go ahead and tell them that angle OTS is 90 degrees. Angle OTS is therefore equal to 90 degrees. But we can also see that in this quad, okay, is the interior angle and that is the exterior angle. Okay, so interior opposite angle. So because they are equal, we're just going to conclude that they are equal. OVP is equal to OTS. And so because they are equal, we can finally just conclude that this is indeed a cyclic quad. So VOTR is a cyclic quad. And the reason it is a cyclic quad is because we can't really say we use this theorem, but rather we're saying we use the converse of this theorem, because you're not stating that this shape is already a cyclic quad, therefore the exterior angle of the quad is equal to the opposite interior angle. We are saying because the exterior angle of this quad is equal to the opposite interior angle, this is therefore a cyclic quad. Okay, so we're just proving that quad is actually cyclic. So we can just say this is because of the converse of the exterior angle of a cyclic quad theorem. Okay, so that is our answer for that question, and moving on to the next question. Question 7.2 says, prove that OR squared equals OV squared plus TR squared minus RU minus TR all squared. Okay, so the only way we can actually get this is we have this figure. Okay, so I'm just going to pull this down. Okay, so here is our diagram, and let's go. So they say OR squared. Now with these ones, you can see that this type of situation, it's kind of created to confuse, or not really confuse, but it's meant to train your focus. Okay, they want you to see how you can just focus on getting to the answer. And with Euclid, I always say that never guess, never find random things if there's no reason to find that particular thing, and always create a strategy. So with this, I don't want to start trying to find out why did they give me this yet and all of that, because then I may just get lost with all these letters. And so what I'm going to do is focus on what they said. They said OR squared. So I'm going to look for ways to construct finding OR squared. Okay, clearly because they're saying squared, they are probably using Pythagoras. We can see 90-degree triangles all through here. Okay, there's a right angle triangle. This is also a right angle triangle. This is also a right angle triangle, because if that's 90 degrees, this is 90 degrees. Okay, that's not really something you need to even conclude, because this is perpendicular to that. Okay, so let's focus on OR squared. Let's see. So what they clearly used is OR squared. And let's look at the ways to construct this. So OR is this. So from this, you can clearly see they either used this triangle over here. And if we use that triangle, OR squared would be equal to OV squared plus VR squared. Okay, and that would be using Pythagoras. But we can't just go with that and say, okay, that's definitely what they use. Let's go with that. There's also another way to find OR squared. We could find OR squared by simply saying, use this triangle over here. Okay. And if we did that, we would have to say, since this is the hypotenuse squared, you would say OT squared plus TR squared. Okay. Now, in all of these, I should not forget to say theorem of Pythagoras because we still need to give reasons for our answers. And now, let's make our decision. Which triangle are we using? This top one here or this one here? Okay, so based on the way this is structured, it looks like we could use any of them, but I won't really dwell on that so much. I won't really say that we can just use any of them because one triangle has a lot of the sides that they're mentioning. Okay. So do you see how with this, right? Let's say we went with this one. You've got OV squared plus VR squared. Look at OV squared over here. So what that would mean is they said OV squared and then VR squared is somehow equal to everything here. And then you're just going to have to find out why it's equal to that and then show them that. Okay, so but with VR, I will not go with that. And here's why. Look at where VR is. To be honest, it doesn't seem like there's much that you can do with VR. Okay, it's just there. It's over here. It's not interacting with the other sides. So now I'm going to rule this one out. Okay, and you should just always go with your gut feeling when you just look at it. Not really gut feeling, but just based on that. Okay, you can see that VR doesn't really have a lot to do with all the other sides. So let's let it go. Let's not dwell on it too much. And we're going to use this method. So let's see how we can get to this. So with this method, what they would have said is OT squared plus TR squared. So let's look. Do we have OT or TR here? Yes, we do. We have TR. So clearly they said, and I'm just going to maybe put it like this. We've got TR squared. And so somehow all of this is equal to OT squared. And we need to find out how that is possible. So let's find OT squared. Okay, now at this point, this is when you can start actually looking at these, because at the end of the day, you just need to find out why all of this is actually equal to OT squared, and then we'll be fine. Okay, so let's just go ahead and highlight what we are using. Using all of this. This should help us to just decide. Okay, OT squared, how is this equal to OV squared minus all of this squared? So the first thing I'm going to actually just straight on go to and just see what exactly is going on here. How did I get this? Let's look at RU minus TR. RU minus TR. Do you see that if you take this entire length, right, and you say minus this, what are you left with? TU. So that they're referring to, okay, this RU, that is actually TU. So we know that TU is actually equal to RU minus TR. We'll keep that in mind. Let me actually make this shape smaller because I need to put reasons down and I don't want to not have any reasons. Okay, so it means that you see this OT that we keep, we're just trying to find, that OT squared was actually equal to, since we know that all of this is actually TU, it means it was equal to OV squared. Again, this is TU, so minus TU squared. And let's see how possible is that. OT squared, okay, OT is over here. Can it be equal to OV squared minus TU squared? That wouldn't make sense because OV is over here. But look at OV. OV is a radius from the center to the circumference. So maybe it wasn't OV they used. Maybe it was OS. So instead of OV, they probably used OS. See, lots of things to take into account here. So here I'm going to say, but I can clearly see that OV and OS are equal. Okay, and this is because they are equal radii. So let's look at this again. Okay, so OT squared is actually equal to, and then in place of OV, I'm going to say OS. So OS squared minus TU squared. And let's see how possible that is. Okay, Okay, so OT squared is equal to OS squared minus, we can clearly see it's not minus TU. If you're using the theorem of Pythagoras here, right? OT is one of the shorter sides. OT squared would be equal to the hypotenuse squared, OS squared, which is true, but minus ST squared. Okay, so that means there's a relationship between TU squared and ST squared. Let's look at that. Do you see how ST is exactly the same as TU? So that's where they got that from. So now I'm going to include it again. So we could have stated it here. You could have said, but let's just follow it step by step. And then I see, and I also see that TU and ST are exactly the same. So let's update this equation so it actually is correct. So it means that OT squared is actually equal to OS squared minus ST squared. Okay, because we see that those two were already equal. So these two were equal because it was given. Okay, so we have those things down. And now we can see what OT squared is. Okay, OT squared is actually equal to OS squared minus ST squared. Okay, so this is clearly the equation it came from. But then now remember the focus is on OT squared. We're trying to find out why is OT squared equal to OV squared minus this. Okay, now this makes sense now. This RU minus TR all squared, that clearly came from ST. Okay, so you see how RU minus RT, okay, is actually equal to TU. But then we found out that TU is equal to ST. So we know that, okay. But then this still needs to say what this is saying. Okay, so we know that they clearly replaced it by using ST. So the whole goal, it's this equation that this came from. Okay, so this is clearly where it all came from. I feel like this is where I should have started and then, proven from there. So this was because this is, because of the theorem of Pythagoras, we can see that OT squared really is equal to OS squared minus ST squared. But clearly what they have done here is, you see, we need to show why OT squared is actually equal to OV squared minus all of this. Clearly, the OS, they actually still replaced it with OV. Remember how OV and OS are exactly the same. So we're going to do the same thing here. So we know now that this equation for OT squared can actually be expressed as, instead of OS squared, we're going to put OV squared back in there. So this is OV squared in place of OS because we know they are equal, okay, equal radii, and then minus ST squared. But you know that ST is equal to TU, okay? So because it's equal to TU, and you remember that TU was equal to RU minus TR, in place of ST, we can just replace this with RU minus TR, and then all squared because it was ST all squared. So this is where it came from, okay? And so they were able to see that, okay, all of these things are equal to these, and that's where that came from. So now we actually have an equation for OT squared, and that was the whole goal. We needed to find OT squared, and now we can put it back into this equation of OR squared. I feel like it should have been, I could have proven it in a neater way, but I was just trying to think it through like that. Okay, so finally I can show that OR squared is equal to, and so that is going to be, let's just add them together. So OR squared was equal to all of this. So that was OV squared minus RU minus TR all squared, and then plus TR squared. So plus TR squared. And all we have to do is rewrite it the way they did. So this was OR squared is equal to, do you see that all they did was they wrote OV squared first and then the TR. So OV squared, there's our positive TR squared, and then minus, okay, that RU minus TR all squared. And there we have proven this. So there we go. Yeah, okay, so that is it. And that is it for question 7.2. And that is it for question 7. Okay, so that is the last question for this paper. And that is the end of this paper. If you guys have any questions, please do leave them in the comment section below. And I hope to see you guys in the future videos.